Good evening, all. Welcome to another session of uh, live session for the NPTEL course on urban utilities planning, water supply, sanitation, and drainage. One second. Just check something. Right. So, the course instructor is Dr. Devapratim Pandit. He is an associate professor at the Department of Architecture and Regional Planning at IIT Kharagpur. I am Monica S. I am a research scholar at the same department. So we have two means of interactions in these live sessions. One is the weekly live session every Monday from 7 p.m. to 8 p.m., where you can, as and when a question is done or a set of questions are done, once I prompt, you can sort of raise your hands, unmute, and raise a query, or you can post a query in the chat box. We also have a discussion forum where questions can be raised, which will be addressed either by me or by the main NPTEL team. Right. So, week 8 majorly focused on water carriage systems. The first lecture was an introduction to the water carriage system and sewerage layouts. Then we moved on to quantity of sanitary sewage, and we also saw stormwater drainage planning. Right. So, in today's live session, we'll be looking at a few assignment questions from the previous run of the course. There is one numerical question, if I'm not wrong. We'll also be looking at some relevant general content, both in between as well as towards the end, where I want to introduce probably one urban planning tool that I found to be very interesting, that I came across during a workshop. So let's move into the session. First question of the day. Match the following water carriage system with its functions. So we have three systems mentioned: combined system, separate system, and partially separate system. Uh, any guesses or any answers rather? What do you think the combined system is, if you remember from the lectures?
A is the right answer.
Okay, so A is the answer being given. So A matches combined system with option 2, carries both sanitary sewage and stormwater. B,
Yes.
separate system is domestic and industrial sewage is carried out in one set of sewers, and stormwater and solid surface water in another network. And C, partially separate systems with basically portion of stormwater is allowed to enter the sewers carrying sewage. Okay, you are actually right, ma'am. So let's take a look at a few of the basics. I think I'll delve a little bit into the details. So as you can see from the slides, we had the options basically lifted out of the slides. Let's look at the combined system first. So this is a typical layout. This is not necessarily exactly how it is going to be in the city. However, it sort of represents the basic concept or the fundamental principle of how these systems work. So in the combined sewerage system, so you can see that sewage is sort of coming in into the sewage and stormwater drain, which is called a sewerage. So I think I had previously also highlighted this point. There is a fundamental difference between sewage and sewerage. Sewerage is the network of pipelines that is carrying sewage. Sewage is the liquid waste that we are talking about, right? So in a combined sewerage system, basically both sewage and stormwater are carried in the same pipeline, right? So we have two inlets that are shown here. There can be multiple inlets. So sewage comes in through these pipelines from the households, whereas you have the roof drain water from the roofs collected and delivered through a network of pipes. And we have stormwater drains. For example, we have these grills located at the sides of roads, or sometimes they're even located on this side, right? So they sort of trap the water that is flowing, and then they also direct into the same line. So what happens is, essentially, the water level is low, right? So which means all of the water, both the storm drain water entering the storm drain, as well as the water entering from the pipelines, from the houses, from the WCs, or the sullage even, is being taken in this pipe itself. However, when there is a heavy rain, I think the next one will be more representative, right? So here you can see how this is sullage, right? And occasionally there is also some water flowing into these, or during light rains, say, for example, there will be water pouring in, and most of the wastewater will be going to the treatment plant. The expectation is that most of the siltation will sort of happen in the bottom of this, right? So this is very representative. So don't wonder if it is going underground. It's basically showing it in two different directions, right? However, whenever there is an overflow, so here sometimes if there is an overflow, it might go over, but most of the time the water level will remain below this dam, right? However, when there is very heavy rainfall, what happens is there'll be an overflow into uh, river bodies or some other surface body where the outlet is positioned. So in fact, the advantage of the combined system is that the siltation that happens in pipelines usually gets washed away automatically during wet weather. However, you can see how during heavy rains, or some sort of, in areas where they have snow, uh, if there is a heavy precipitation, there is always a possibility that sewage water also goes into river water and gets sort of pollutes it. So that is a negative, in fact, which is why the combined sewerage system is, I mean, it has its advantages and its disadvantages, right? So we also have two other systems: separate system, partially separate system. So the separate system, essentially, you have two pipes. Pipe number one is for all your sewage and sullage coming in from the households. So that will be connected to the main sewerage line, and you'll also have a separate stormwater drain system where all of the drainage happens here, and it usually is outlet into a nearby water body, right? However, the issue here is that siltation. So there is something called a minimum self cleansing velocity. So self cleansing velocity is when the pipe can sort of clean itself and doesn't allow for siltation. Even if siltation happens periodically, what ends up happening is the gush of water that comes in at intervals or seasonally sort of clears up all of the siltation. So that's the idea behind having self cleansing velocity, which might be lacking in a separate sewerage system, right? Especially in areas where the water supply. So again, if you remember from the lectures, the amount of waste generated is, especially in terms of sewage, is sort of dependent on how much water supply happens to the house, right? So in areas where water supply is quite less, then the separate sewerage system sort of suffers from siltation, right? So whenever, I mean, at the building level, when there is a combined system, what happens is both the wastewater and the rainwater. So if you remember our site plans, we sort of give an outlet for the rainwater also from both the site as well as the roofs collected. So it is both left into the same uh, pipe, so same ferrule. However, when there is a separation, you have two separate lines, right? So this is the stormwater drain and this is the wastewater drain. Right. So when it is a partially separate sewerage system, the thing is, this is only one option. Okay, this is not necessarily the system that is always there. One option is you have the sewerage and sullage coming in to the sewer system, and one part of precipitation. So here we are actually seeing how the roof drains are all connected to this. So in the event of rainfall, this sewerage system sort of gets cleaned, right? And in case of heavy rainfall and there is an overflow, Yes, it allows for so that the STP is not overwhelmed. Imagine carrying this much water and treating them. So that the sewage treatment plant is not overwhelmed. We sort of have an overflow mechanism where the excess is let into the streams. Right. However, you also have a drain system. This need not be the case. So it might so happen that so this is the easier way, but some places might have partially some of the stormwater drains also connecting to the sewer lines. So that is your partially separate sewerage system. So the answer is right, as Ms. Supriya pointed out. The answer is A. Any questions regarding these three systems? All right. So moving on to the next question. Sewage lines are installed in a vertical zigzag configuration in A. Pressurized sewer system, B. Vacuum sewer system, C. Partially separate sewer system, and D. Combined system. Any answers?
It's a pressurized sewer system.
Okay. Okay. We have one option. Anybody else?
Confused in pressurized and vacuum. Let's
Okay.
see.
So the answer is actually B. Vacuum sewer system. If you remember from the slides, since so you can see the setup here from the slides, right? So you have a vertical zigzag sewer line that is present in this system, right? So the answer is actually B. But let's take a look at some of the mechanisms of a vacuum sewer system, right? So this is a typical vacuum sewer system. It's from a private company abroad named Fluvac. So if you see in this diagram, you have this collection tank, and then you have these vacuum pumps, right? So, and then there is another collection tank, which is sort of the main storage from where it is sent again to the to treatment, right? But there is always this separate collection pit. Here we've called it sewage pump, but these people are basically calling it a collection pit. The functioning is essentially the same. Yeah, I can't. One second. Yeah. So what happens is once the sewage sort of fills into the pit beyond a point, it gets sucked out. So it sort of is a trigger for the entire operation to happen. So you can see it again. So after this point, after this level, the suction starts, right? So this is just a photo of somebody trying to maintain the pit. So from that pit, essentially a vacuum interface valve. So this is the valve that sort of enables the suction happening. So because of this, the movement of this canister of sorts here, what happens is it creates a vacuum and therefore a flow into the pipeline. So that is the basic setup that we have. You can see how there is usually another storage tank, and this is that valve that we were talking about. So and you also have a monitoring station where the functions are monitored. So that's the basic setup of a vacuum sewer system. In case of India, recently around April, there was news that Agra is sort of planning to install their first vacuum-based sewer system. It's actually for a small collection of units that are in a low-lying area. So there was difficulty instead of going for a huge uh, network system where the topography essentially made it tricky to install a conventional storage network. So if you can see here, so it's about 112 chambers have been made. So all of these are in a low lying area. They also have the sensor that we just saw. So beyond a point it sort of gets sucked out, and we don't have to worry about the pipeline being or the system being constantly in pressure, because there is a trigger mechanism, right? So it sort of controls the entire system, and it's all pneumatically operated. Pneumatically as in essentially through the presence or absence of air that creates a vacuum, right? So that's something that is there in the news, that is relevant. Moving on to the next question. Any doubts about that? The vacuum sewer system before we move on.
No.
Okay. All right. So moving on to the next question. Design infiltration value shall be limited to a maximum of dash percentage of the design value of sewage flow. Is it 5, 10, 15, or 20 percentage? Any answers? This is something that was directly mentioned in the presentation as well, the lectures. Okay, the answer is actually, okay, we have one answer C. The answer is actually B, 10%. So if you can see in the slides, we shall limit it to a maximum of 10%. So that is something that we are doing. It might end up actually being higher than that, but that only means that the system needs to be rectified. So this is sort of the upper tolerance limit for any sort of infiltration to be allowed. Right? Infiltration essentially comes from some sort of crack or issue within the mm, pipeline system, right? So the answer is B actually, right? So moving on to the next question. Which of the following does the peak factor of sewage flow depend on? A, population; B, population density; C, site topography; and D, water supply hours. Any answers?
It's D, A, B, C, D, all D option.
Okay. We have one option in the chat box as well. Okay, so the answer is actually D. So I understand that these three are the ones that are mentioned here, but the flow in sewers varies depending on the water supply hours as well. So the peak supply rates. So the slide also mentions how to consider the peak supply as well based on population, but it basically also is influenced by water supply hours, right? So the answer is actually D. Right. So moving on to the next question, which is also sort of a direct lift from the lectures. Flow rate at night is dash percentage of the average flow. 40 to 50, 50 to 60, 60 to 70, or 70 to 80. Any answers? Okay, we have one answer in the chat box, C, 60 to 70. And you are right. So it's again given directly in the side. So these are numbers that you sort of need to uh, remember. These seasonal maximum, monthly maximum, daily maximum, or the minimum flow, and such numbers are something that you need to commit to memory. Right. So the answer is C. You are right, Mr. Rahul. Right. Moving on to the next question. Which of the following method is involved in intensity duration frequency curve generation? Which is the IDF curve generation. A, Bernard equation; B, time area method; C, unit hydrograph method; and D, rainfall runoff processing simulation. Any answers?
Bernard equation.
Okay. Yes.
Bernard equation A.
We have two answers, and both of you are right. So that is the Bernard equation. Essentially, this is the formula for Indian conditions, right? So it's the coefficients, the intercepts are derived from existing values. So yes, the answer is Bernard equation, right? All right. Moving on to the next question. What is the partial area effect? I runoff coefficient into lesser catchment area into higher rainfall intensity is greater than runoff coefficient into full catchment area into lower rainfall intensity, or is it lesser than or equal to? So essentially these symbols are the ones that are irregular. Is it lesser than or is it equal to? What is the equation that sort of captures the partial area effect? Any answers? Okay, so if you remember from the slides, the equation is
C is the
sorry.
C option I was
No, it's
saying.
actually
C.
A, right? So I'll sort of
Is there
explain how the entire thing goes, right? So I couldn't really get a good graphic to represent this, so I'm going to go ahead and do my bad drawing. So say there is a drain network, all right, and you have sort of this entire area that is draining into this part. So why is this part draining and what about these areas? What happens is these areas will sort of drain into some other natural or artificial drain. So what happens is, let me draw a cross section here. So say this is the terrain. What happens here is from this point to this point, all the water sort of starts flowing to the lowest point. So say you locate the drain somewhere here, ideally. All the water sort of starts flowing like this, right? So and these anything that falls here will be flowing on the other direction. So that's this area is sort of called the watershed, right? So when you have an artificial uh, sewer network, so say this is our sewer network, right? So and say you have these, again the topography so happens that the water from all of this area is draining into this drain, and say you have an inlet point here, you have an inlet point here, you have an inlet point here, and you have an inlet point here. So what happens is all of the water sort of starts draining into it, right? So in order to understand this partial area effect, it's actually more complicated than it this equation captures. So what happens is, let's consider this part, right? The last in the drawing, the last part, this part of it. In this part, everything that drains in goes here. In this part, everything that drains it goes here, plus whatever is flowing through the pipe, right? That part is also part of the inflow into the at this point, right? And everything that is flowing into the pipe, so everything from this whole area is going to flow into this part, and then from everything from this entire region is sort of going to flow into this part, right? So this entire region, the expectation is that it's going to flow into this part, right? And you have this tiny, I'm going to use another color just for representation, and you have water flowing from this region as well into this point, right? So what would our expectation be? We are going to design the sewer line based on the maximum expected flow through the sewer line, rather stormwater drain line, right? So the drain line's cross section will be determined based on how much water is expected. So the standard expectation would be that the blue area sort of will be much higher than the green area. Why? In basic math, the amount of rainfall for a particular intensity is going to be, say the intensity is same in both areas. Then you would expect that this big area is sort of going to contribute more, which means the flow inside this will be majorly determined by this, right? However, imagine a situation where the blue area is highly pervious, right? Like most of the water that's falling is going to flow in, and say the slope is also very gradual. So, which means the amount of time that is taken from the farthest point to reach this drain, say in this case, from the farthest point to reach, sorry, you get the idea, from the farthest point to reach this drain is going to be very high, right? So the amount of time it takes is going to be high. Why do we care about the amount of time? Whenever you're designing the cross section, the amount of time that the flow takes, basically the pipe should be able to cater to the flow, right? So the amount of water movement in the pipe, if it keeps flowing, then say you're designing it for how much ever water is going to come in 10 minutes in this area, and say water is going to take 20 minutes to reach this point, which means by the time this 10 minutes ka water flows in here, this pipeline, whatever that particular section of water, is going to move ahead, right? So it so happens that the pipeline can take much more because of the gradual slope. I hope I'm clear, right? So essentially, three factors. For example, one is the slope, one is the permeability. Say a lot of water falling in this area is actually going inside the ground. It's not even coming to the water body. Versus in the green area, say it's all rock, and say it is very, very steep, which means the amount of time that this water is going to take to reach this point is going to be very quick, right? So the flow at this point will be much higher. So it's like pouring an entire can of water into a small funnel versus having a very large draining body, like a huge funnel which is slowly draining, and it also has holes in it, which means not all of it is really going into the manhole in the drain. Because of these two aspects, it might so happen that the smaller area of flow should be taken into consideration rather than the bigger area ka flow in determining the cross section, because this amount of water is going to be so huge that the pipeline should be able to take that into consideration. So that is basically known as the partial area effect. Am I clear to I mean, is my explanation clear? This is like the simplest way of explaining it without going into the dynamics of water flow. Or is there any doubt? I hope like you get the basic idea, right? Like it might happen. I'm not saying it is necessarily going to happen, but it might happen that higher rainfall intensity in a lesser catchment area in a small part might be greater than full catchment area. So the entire area with a lower rainfall intensity. So also depends on the intensity of rainfall. Say the intensity of rainfall so happens to be lower in the blue area and higher in the green area. Like rainfall is not uniformly distributed geographically, right? So how does this matter? Like, why is it going to be a problem for us? So the answer is A. Let's go. So there, I'm just showing an example. Again, please don't go into the details or what does CO mean. What? Let's not go into the details of the solution. I'm just going to highlight a couple of points regarding the partial area effect alone. Right. So there is this software called Connect that's used to design various drains. So here the polygons represent the catchment area, right? And the lines are conduits or the drains where it is flowing. The boxes are inlets where the water is actually flowing into the drain, right? So here there is an option within the software where you sort of switch off for partial area effects. You can see how uh, the flow in this conduit is 7.43 liters per second, and then so the runoff from this is 7.43 and it's flowing completely, and then you have this huge runoff of 46.75 from the catchment area 2, which is flowing into this inlet, after which the flow is actually 25.70. So it's not exactly half but almost half, so it's also accounting for losses and other aspects, so which is why I'm saying it's not going to the details, but essentially it's becoming half of the flow, right? However, if you actually account for partial area effects, as we said, the flow in this is very low, and then there is a huge runoff coming in, which means the flow in the channel that needs to be taken into account is actually much higher. If you actually have the same cross section, it's going to be close to the runoff that is coming into from this catchment, and that's known as the partial area effect, right? Which means if your pipeline cannot handle that flow, you'll have to create a much bigger diameter from this point or gradually from this area, right? Which means the cross section of this stretch of the pipeline needs to be modified. So that is why we sort of take the partial area effect into consideration. So even within this software, the partial area effect comes into play only if this combined number is lower than this inlet number, right? So this is known as the rational flow. Rational flow is basically what is already coming in through the system, and conventionally sort of, sorry, not this number actually. So this number and this number are compared, and only if this number is higher, this flow is taken into consideration. If this number, say this ended up being actually something around 60, then this number will be taken into consideration for the design of the drain from this point. Am I clear? Are there any doubts till now? I hope that sort of, like, that makes it easier for you to remember, right? Like this entire part about lesser catchment area, higher rainfall intensity could still be greater than full catchment area, lower rainfall intensity. That's whenever that comes into play, that's known as the partial area effect. It does not always happen, it might happen, and it needs to be accounted for. Like, you need to check for it, basically. All right, moving on to the next question. Design of pumping station depends on A. Space availability, B. Distance or route of the rising main alignment, C. Estimation of design runoff at the pumping station, or D. Capacity of the wet well, that is detention time in minutes for peak load and additional storage capacity, essentially storage capacity. Any answers? Okay, we have two answers in the chat box. One is D and one is A. Anybody else? Okay, the answer is actually D. If you they're a direct lift off from the slides again. So space availability is something that we need to consider. Uh, Distance or route of the rising main alignment. So Basically, if the distance is too much, say your households or your settlement ends here, then your STP somewhere very very far away, this is your settlement. So what happens is, by the time the say the sewer line is here, by the time it comes here, the velocity is going to be so low that the flow of sewage is going to be low. The thing is, once more sewage comes in, flow might be good, but siltation might increase. So even to avoid siltation, as well as uh, to make sure, say the route has some sort of bend or anything, there at these points or somewhere right before it, we have a pumping station to sort of boost the flow, right? You push it ahead. So that is why we consider distance and route also. Then design runoff at the pumping station, yes, and capacity of storage, right? So if the STP capacity is going to be sort of low, you can have a storage and then pumping, right? So the answer is in fact D. So this is a typical image of a pumping station. So you have these huge pumps here, and you have these, if you can see the airplanes, right? So sorry, the so it sort of flows in and then it's pumped ahead. I wish I had a better photograph. Unfortunately, I don't. So sometimes you also have such setup. So this is an interesting setup that is that is there in Trichy in Tamil Nadu. What happens is, these pumping stations also have these additional inlet points where fecal sludge from the households. If you remember from the previous session, how fecal sludge management is also something that we need to consider. So usually these tankers that sewage tankers that take fecal sludge from the households go and dispose it off in drains or some sort of open water body, not just due to the lack of, it's not just out of, I don't want to do it or I'm lazy, but sometimes it's just a matter of they don't know where to go and dispose it off. And the water treatment plant might be very far away, and all of these problems are sort of nullified when you have fecal sludge added into the sewage right before pumping. So that way they have access within the city, they don't have to travel all the way to the STP, and that's also saving time and fuel and other costs. So this part is also pumped essentially into the sewage system. It also helps dilute the FSTP, or rather fecal sludge management is has a slightly different composition, right? But because of the quantity of sewage that is going in, this might end up diluting the composition of the fecal sludge as well. So it has multiple advantages, right? So going on to the next question, which of the following is not a component of capital costs concerning stormwater drainage projects? A. Cost of civil construction. B. Cost of pumping machineries and their installation. C. Cost of drain appurtenances and erection. And D. Cost of chemicals. Mind you, it's not a component of capital cost. Any
Civil
answers?
construction.
Sorry?
A. It's A.
Okay. We have one answer, A. In the chat box, we have two answers, D. So the answer is actually B. So anything that is going to be so this is there are two types of expenditure. This is not just in infrastructure, in general terminology. Anything that is sort of going into some sort of permanent structure. Say you are buying a plot of land to do something, or you're buying infrastructure to you're constructing something, you're investing in a factory, you're investing in the infrastructure that is going to provide something, which is civil construction, pumping machinery, enabling them, installation, drains, and again installation of the drains. They are all sort of things that are not going to be immediately expended, right? Like immediately used off. They are going to have a longer period of time to which they are going to sort of stay. So such expenditure is called or rather such utilization of funds is called capital cost, right? Whereas expenditure, the term expenditure is anything that is going to be used up. For example, chemicals. Once you use them, they are not really going to stay, right? Like it's, for example, if when you buy a house, that is a capital cost, but when you buy furniture, that's capital cost, but daily expenses are all expenditure, right? So that's sort of something that you can keep in mind to categorize the two. So our capital cost includes civil construction, cost of drains and appurtenances. One second. Am I still audible? Can someone post in the chat box? Yeah, okay, all right. I think I had a glitch. I just got a message there. Thank you. Okay, coming back to the presentation. So, yeah, the answer is therefore D, right? One second. All right, so moving on to the next question. So, this is the numerical I was talking about. What is the rainfall intensity for a storm of 15 minutes duration using empirical formula in absence of rainfall records? A 30.48, B 32.48, C 33.48, or D 34.48? Any answers? I guess you can't sit and calculate now. So let's just go to the solution. So we'll be using this empirical formula for rainfall intensity when we don't have availability of rainfall records. So what is given essentially that the duration of storm is 15 minutes, and there is an absence of rainfall records, and we need to find the rainfall intensity of the storm. So we'll be using the empirical formula. So which is essentially 25.4 into A divided by T plus B. So you can see T is the duration of storm in minutes, right, which is given to us 15 minutes, and the value of A, okay, yes, Mr. Rahul, the answer is actually 30.48. Thank you for that. So I'm glad to know somebody is sitting and actually bothering to calculate. So the answer is basically the value of A and B are basically depending on how much the duration of storm is. So 50 to 20 minutes you have A is 30 and B is 10. And for any duration of storm between 20 to 100 minutes, A is equal to 40 and B is 20. So these are empirically determined for the Indian context, right? So A is 30 because we have duration of storm that is less than 20 minutes, and T is 15 as given, and B is 10. So you substitute the values, you get 762 divided by 25, you get an answer of 30.48, right? So that's our answer. Any questions? It's a very simple problem. Okay, I hope not. So that's basically it from the previous assignment questions, but I would also like to share some general content. So this is something that I came across in a workshop conducted by IAHS Bangalore. It was in collaboration with the Tamil Nadu urban sanitation program, sewerage and stormwater, some the PNUSSP program. Sorry, I can't remember the full form. So they introduced us to this very tiny software called a shit flow diagram software. So essentially, it generates an excreta flow diagram for the city, right? So you sort of can use it to both estimate and to communicate how does the sewage in a city actually flow through the system, right? So I'm going to go ahead and open the website. So this is the website. It's sfd.susana susana.org. So I'll open the So it's actually Susana is the Sustainable Sanitation Alliance. It's an organization that's essentially working on promoting sanitation. So this is the SFT graphic generator. So I'm going to give an introduction to how it works. You can actually go ahead and it's a very simple software download and available for download. So you can always play with existing cities. So I'm just going to go ahead and select New Delhi. And then you can see how the city's shit flow diagram actually looks, or you can also create your own graphic. So the first table that you'll be looking at is so where does the toilet discharge to? So how is the sewage? Where all is the sewage going? So there are multiple options. There is no on-site container. If there is no on-site container, then where does it go to? If there is a septic tank, so even if there is a septic tank, it goes to open drain or storm sewer or to open ground, or it does not even go anywhere. So this option is not applicable if it is essentially going to the septic tank, right? So then there is a fully lined tank. So you these are the options that you have for the city, and you can sort of highlight which ones are present in the city. Once you highlight them, you can go ahead and give the detailed numbers, right? All of these is going to be determined based on surveys or some sort of uh, secondary data or through a primary survey through fieldwork. So you can enter the proportion of the contents of each type of on-site container, which is fecal sludge. So how much is the fecal sludge divided into? So how for 50% of it is septic tank, 50% is seal tank. So you give the numbers. You can also seek help from this software itself as to what the numbers correspond to, right? Then you can just create your SFD matrix, and essentially again these are numbers that you can modify, right? Because proportion of population which is using that type of system, you need to enter this value. We can also get these values partially from the socio-economic caste census, SECC. The latest round has not been released, so the numbers are probably based on the previous round, right? So then you can also see how much proportion of wastewater is in the system. So once you give all of these details, it sort of gives you this graphic where the overall number is also generated. Essentially, so this is a graphic for New Delhi, and according to the numbers, 56% of the sewage is properly handled, but 44% is sort of unsafely managed, right? So WW is wastewater here. You can see the key here, right? FS is fecal sludge, and SN is supernatant. Supernatant is essentially the af- when you take fecal sludge or rather sewage that settles inside a tank, you have two components. One is the sludge, that's the settled part at the bottom of the septic tank, and then you have the water above it, right? So that's called the supernatant. Uh, the watery part usually is originally allowed to seep into the soil after a particular duration, so that it's filtered and uh, it infiltrates into the soil. So in this case, you can see how, like, it also shows the rough proportion of water that gets mishandled at each stage, right? So I thought it was a beautiful way of representing how the entire mechanism works, and you can sort of use it to either make your case, or you can just play around, check for other cities, like say for Trichy, the according to the this person's report and the numbers that have been input. So 60% of it is being handled properly and 40% is not. And you can also save the data in multiple formats, which is also very interesting. So, right. So I just thought I'll share that with you because it's something that I found to be really useful. So that's all for today's class. Any doubts? Any general queries? Right. So if there is nothing else, I hope the additional material is also useful. Usually in urban planning, essentially it's all about decision making, right? So how do you decide? You need to have some form of guidance tool where you can use to take your decision, that you need to base it on. So instead of making very arbitrary considerations or basing it on just qualitative knowledge, if you can somehow crunch numbers, then that's one way of going it. However, the qualitative knowledge also is essential, because otherwise you wouldn't really know the problem. You're probably shooting in the dark, right? I mean, the absence of a toilet, for example, could mean so many things. Are people not comfortable with the technology, or are people too poor to construct? Is there a lack of space because the units are very old? So what is the issue, like, or is there the problem of safety? This is something that is very common with community toilets, for example. When there is a small pocket of households that don't have a toilet built in, so they all use a community toilet. What happens is the very lack of security does not permit everybody to use the toilet. Uh, Toilets that are built and maintained properly, or there is a lack of maintenance, or sometimes it's a matter of social taboo, right? It need not be something as big as, yes, waterless, absolutely. Essentially, these installations also have troubles with themselves, because some people just don't like the idea of a waterless toilet, right? I mean, they are just averse to the idea of not having a hand flush, so therefore they don't use it. So we really need to delve into the basis of why is there an issue in a particular area. So both the quantitative and the qualitative aspects come into the play in terms of planning decisions. So essentially you can also see how interdisciplinary planning is. So all these multiple considerations taken in is when you sort of take a planning decision. Right? And this is just an introductory course. If you notice, there are aspects such as, if you remember in the IFD diagram calculation, there is a huge chunk missing as to how do we extrapolate, right? So all of these parts are detailed technical issues that you will encounter if you actually, go to the point of, there are multiple ways of extrapolating and regression methods that you can use. However, you should know that it is possible for you to even employ it. So this course is all about introducing you to what is usually done, what is the basic framework of working, right? So if there are no other queries, I think we can call it a day. I hope it was useful. And if there are any other softwares or resources, any such interesting, simple to use but yet very effective tools, you can always share with the class, either in the discussion forum or in one of these live sessions. You can just post it in the chat box. I'll also be happy to. Thank you, Mr. Rahul, for feedback. Thank you. All right, then we'll call it a day.